So let's get started. Welcome to this talk. My name is Lenny Zeltzer, and I teach the reverse engineering malware course at SANS. And I thought it would be fun to put together this short presentation introducing people to key aspects of malware analysis. Because I know there are many out there that are wondering, what's that about? Is that accessible to me? How much do I need to know? What are the key tools and techniques that people use? And that's the goal of this talk, to introduce you to these concepts and these tools. Of course, my hope is that you're going to feel inspired by what you learn here and will want to continue learning. But also, I want to give you some very specific and concrete recommendations for what you do if you do come across malware in your organization. So that's really the goal of this talk. And it's really interesting how prevalent malware has become as part of most incidents that we're dealing with. Whether there's an outsider or an insider, whether it's a stealthy attack or blatant defacement, in many cases, malware software, malicious software is part of those incidents. So it is important for forensic analysts, system administrators, incident handlers to know how to deal with it if they do come across it on their systems. It's kind of hard to do because malware, what can it do? Well, anything that software can do, except not for good, but for bad. So how do you analyze malware? Well, same way you analyze software. It's not easy, but the nice thing about this field is that tools are becoming more and more mature, techniques are becoming more and more developed, so that it is becoming more and more accessible. So that's kind of nice. At the same time, it's still exciting enough that there's a lot more research that can be done, and so you really can make your mark if you decide to pursue this area of your career. And really, I think it's important to know how to deal with malware if you do come across it in your systems. You don't need to be a malware analyst expert, but it's nice to know at least how to get started. And perhaps this session will help you determine how to get started. The course that I teach at SANS, it takes the dual-phased approach to malware analysis because that's the approach that works well for me. You know, people that want to learn this topic come from various backgrounds. A lot of people have some programming background. Maybe they do it now. Maybe they took a programming class in college. But a lot of people who take this course are people who have a strong systems and networking background, not much programming, though. So that's why there are these two phases that we follow. And I'm going to give you a concrete example today. I'm going to show you some interesting analysis aspects of a malicious executable. We're going to analyze a Trojan copy of Microsoft Instant Messenger. It's got some interesting backdoor functionality, and I'm going to show you how to figure out what it can do. And the two phases that we're going to follow will be behavioral analysis, and that is reviewing how this malicious program interacts with its environment. How does it change the local file system on the infected system? How does it communicate over the network? Does it touch the registry? Those are the kinds of questions we ask when performing behavioral analysis. And also, we're going to do some code analysis, because there are a lot of interesting questions that are worth asking and answering by looking at the code that comprises the malicious executable. And there are some tools that can really help us with that task. So that's what awaits us. We'll do a bit of behavioral analysis. And so those of you with systems and networking background, I think will feel right at home. And then we'll do a bit of code analysis. We're not going to go too deep into it, but it'll give you a sense for what it's like to look at the malicious program at the assembly code level. So here is our adversary for this talk. It looks like a standard Windows Live Messenger, you know, the client that you use to talk with people who are on the MSN chat network. You've got your key components here, the logon screen with a username and the password that you need to supply. You can save it if you want to. You can sign me up automatically. It looks just like the real thing. But it was found under suspicious circumstances in a box that's likely to have been compromised. So let's say you get a copy of this executable. And by the way, the slides that I'm using in this talk, you can download them from my website. I'll have a link later on. And you will also be able to download a copy of this malicious program from my website. So if you want to repeat these steps in your lab, you're welcome to do that. And I'll give you instructions for how to do that. So you got a copy of this executable. You put it into your lab, and you're starting to wonder, what is that program about? What is it capable of doing? So the way we're going to approach behavioral analysis is we're going to set up an isolated environment. The reason it's isolated is because you're dealing with malicious software whose one purpose in life is to do something bad. And so you really want to be careful about how you isolate it from the production network. There are several ways of isolating the software from the production network. The most reliable, physical air gap. Don't connect it to the production network. That means having a bunch of systems networked together. If you're using physical systems, it's nice if you're one of those people that had the foresight to buy hubs when they were still available for sale. Not the switches, but hubs that make it really easy for you to snip the network and see everything that's going on. It's nice to connect those systems you're going to infect with a hub. But even if you don't, a lot of analysts prefer to use a virtualized environment. So that's what I'm going to use for my demos today. You can use any virtualization software. I'm going to use VMware because it allows me to have an isolated environment. I can actually bring up multiple virtualized systems on a single physical chassis. They can talk to each other, but not to the outside world. And so I'm going to show you the lab that I set up using VMware. So the idea behind VMware, of course, multiple systems can run simultaneously on the same box. You can have Windows XP, Windows 7, Linux, as long as it's an x86 compatible operating system. And nowadays, let's face it, most of them are x86 compatible. But of course, VMware isn't the only option. You've got Microsoft Virtual PC. You've got Sun VMware Box. Sun VirtualBox. A lot of choices available to you. Pick the one that suits you best. One of the nice things about using a virtualization tool that I thought I'd mention to you, like VMware, is that it allows you to take an instantaneous snapshot of your laboratory state. So before you infect the system, you can click a button. It remembers its state. When you're done with your analysis, click a button. You're back to normal. No matter how you trashed your system, it still looks OK. And that comes in very handy when you can take multiple snapshots throughout your analysis, because then you can experiment with something and not worry about messing everything up and have to start from scratch. It's like a DVR for malware analysis. So very nice snapshot capabilities. I really miss these if I have to use physical systems for malware analysis. And I got to say this, if you do use a virtualized system, be careful about what you connect that physical host to. You want to make sure that you patch up your virtualization software. And I'm sorry, VMware patches are about half a gig in size because you have to reinstall the whole thing. But you know what? We take the good with the bad. You want to make sure it's patched because it is conceivable that malware will try to find a vulnerability in your virtualization software and try to escape to the outside world. And that would be a bad thing for your career. So take care. All right. So here's the first tool that I want to show you. And by the way, I've got these slides, and you can download them from my website, and you can take notes. I've got full speaker notes together with those slides. I'll give you a link shortly. But I also want to actually show this to you live in the lab that I set up just for this purpose. Of course, we know what happens in live environments. Things usually go wrong with live demos. But let's see how this goes. All right. So here's a logo that my lovely wife created for my course. You got to learn reverse engineering malware. That's how I'm trying to compel you to do that. I set up this environment. It is an isolated virtualized machine. It is running Windows XP. And I've got a whole lot of various monitoring tools installed. Various monitoring tools that allow me to observe how malware interacts with its environment. And one of the tools that I thought I'd show you, and we're not going to spend too much time on any single tool, this is a tool called RegShot. RegShot is a tool that allows you to detect changes to the infected system. So the idea is that you use this tool and you take a first snapshot of the system while it is still clean. This looks at the state of your registry and at the state of your file system, and it remembers what it's like now before you infect the box. Then you're going to infect the system, take another snapshot, and use this tool to compare the two. So what I did there is actually took the first snapshot, but I made a mistake. Not because I forgot how to do this, but because I wanted you to learn from my mistakes. You need to enable this option called Scan dir. Otherwise, it will only scan the registry. So I'm going to say scan the file system, not just the registry, and everything from the top of the C drive down. So let me take that snapshot again. It's taking checksums of all the files on the file system, checksums of all the registry keys, and it's remembering them. Not a cryptographic hash. It is possible for malware to try to mess with this output, but realistically, I have yet to see a sample that's trying to do that. This tool just isn't that important. But it works nicely. It's free. It doesn't require any installation. RegShot. Can't go wrong with it, unless it crashes. So let me give it a few more seconds for it to take the snapshot. Once it takes the snapshot, I can be prepared to infect the box. All right, here you go. The second snapshot lit up. I'm not going to take the second one until after I infect the system. And here is that executable that I'm talking about. This is the one that looks suspect, the one that's potentially malicious. How do I infect my system? The way our users do, they just double-click. So I'm going to double-click, and here it is. It feels just like Windows Live Messenger. And so when you've got malware that is prompting you for input, what do? Well, you give it input. You try to interact with it. You try to stimulate it to do something that's worth observing. So I'm going to pretend like I'm a user, and I'm going to try to log in. Let's see, user@example.com. That's my real email ID. Please don't use it. My password is password. And I'm going to try to sign in. Oops, I got an error. What are the chances? Live Messenger is not available at this time. Now, even if this were the real Live Messenger, I actually wouldn't be able to connect to MSN servers because this is an isolated environment. It's not connected to anything. But even if you ran this in the wild, you still would get this error. All right, well, what am I going to do? I'm just going to close. Well, you could try to interact with it a bit more. I'm just going to close it. And now that I did that, I can see it's bringing up a website. The website is ourgodfather.com. Yeah, I'm not sure what that's about. Probably not a good site to visit on a non-isolated system. We're going to not really explore that particular feature of this malware because I want to focus on what this executable is doing locally. Now that I've infected my system, I can take the second snapshot using RecShot. And then I wait about half a minute for it to scan the registry, scan the file system, and compare the two snapshots. Once it's done, the compare button is going to lit up, and it's going to produce a report of all the major changes. Now, the changes, what's going on in my Windows box? Well, you know, a regular Windows system actually changes its state all the time. That's OK. That's normal. For example, maybe a Windows box is looking to renew its DHCP lease. Maybe when you started Internet Explorer, that left a noisy footprint on the registry. So that in itself is not too weird. But let me look at something that looks a little bit interesting, specifically creation of new files. And you could spend some time thinking about why these files were created. You see there are a whole lot of these local settings temporary internet files, probably because Internet Explorer was launched. The ones that look most promising to me are these ones at the bottom. Let me see if I can increase the font size for you. All right, so first of all, this file was created, Windows MSN settings. That looks interesting, but not as interesting as a file called c:/pass. What's it for? Well, let's see if we can take a look at it. So I'm going to go there with Windows Explorer. Here it is. Here's that file. What are we going to find there? Any thoughts? Any suggestions? Probably the password, right, that the user typed in. And here we go. There's the advertisement for this website. For whatever reason, he really wants us to go there. We're not gonna. But here's the username that I typed in, and here's my password. OK, kind of interesting. Not super exciting, because we know that it's capturing our password, but we still don't know how is it, if at all, leaking it out of the environment. So how about the other file that was created? Let's take a look at the Windows directory. The file called msnsettings.dat. Now, I don't know exactly the format of that file, so when in doubt, I'm just going to open it with Notepad. And so what do we see here? I don't know. It's a little bit strange. It's not quite clear what this is about. There's the word hello there. There's a text. Please type in an error message. I'm not quite sure what this is about, to tell you the truth. But you know what is interesting to me? Sometimes when you perform incident handling and forensic analysis, sometimes you're not quite sure what to look for on the infected system. Sometimes it can be hard because the amount of data you're collecting can be overwhelming. So malware analysis really supports your incident response and forensics efforts because based on what you witness in your lab, you may then think to go back to the infected system and take a look to see, hey, is there a file like that on the infected box as well? And guess what? When I went to the infected box, yeah, I found that file. I actually have it zipped up and ready to go in my environment. Let me show you what it looks like, because it is actually a little bit different than the file that was automatically generated. What's in it? Interesting. This used to say hello. Now it says test. Also, here's something interesting. This is the name of one of the many Google's SMTP servers for sending outbound mail. How about this? Looks like an email address, masterkleenex@gmail.com. Well, we don't know for sure, but maybe, just maybe, it's going to email out the password. Of course, this is just a theory, and the thing about malware analysis is that you do end up forming a lot of theories. And so you take careful notes when you perform this kind of work, and every time you witness or observe something that is worth thinking about later, you write it down. And you write down the circumstances under which you observed this. And it might turn out that this is really irrelevant. Or you might find future collaborating observations that really say that this is very important. So that is the thinking process of observing something useful, kind of an indicator, and then looking for other information that will collaborate, that will support this, or maybe prove that this is really irrelevant. So when analyzing malware, I try as much as possible to replicate the environment of the real compromised box. And so the real compromised box, if it had this file on it, that's what I'm going to do as well. So I'm going to take this file taken from a live compromised system, and I'm going to place it into the Windows directory where it was located on the system in the wild. And now I can repeat my experiment. Maybe have a bunch of extra monitoring tools installed, but notice that I'm not just repeating it because I like double-clicking on malicious software. I'm repeating it after I slightly changed the runtime environment of the program in hopes that now I'll be able to evoke additional behavior that's worth observing. That's what behavioral analysis is about. You're not just a passive observer. You really are trying to interact with malware by molding the environment in which it runs. So for this purpose, I'm going to show you another tool. We had RagShot that showed us what has changed on the environment. Now what I want to show you is another tool that can also give you insight into what's going on the system while you're infecting it. And this is a tool called Process Monitor. Process Monitor is a free tool from Microsoft. When you launch it, it asks you, hey, do you want to define some filters? The thing about Process Monitor is that it observes a whole lot of local API activity. Network access, process access, file system access, registry access can be really, really noisy. So I wanted to capture everything, but I wanted to only display certain things for now. So specifically, the filter that I'm going to define is I'm going to say, you know what? I know you're going to capture everything, but I want you to only display those records associated with a process whose name includes the word messenger. My hope is that this is going to cut down a bit on the noise. And now that I'm going to do that, I'm going to click OK, and then it's going to start capturing activity right away if it finds anything relevant. You did not add the item while you were editing. Oh, thank you very much. That's very nice. You do need to remember to click the Add button. OK. Click OK. So it's capturing events. Look, only running for a few seconds, already 5,000 events are in its log file. Fortunately, it's only showing me those events that are associated with the process messenger. And I'm not running the process. That's why it's not showing anything. Let's double-click on this thing. Double-click. Right away, you see the process generating logs. And it's not that strange. Every window executable that's normal is going to leave a footprint on the file system, on the registry. That's normal. So again, we interact with the program, @example.com, my password, and I sign in, and maybe I close the network, and I exit. And then I go back to my tool, and I tell it, all right, enough. You can stop capturing now. I press this magnifying glass button. It'll take a few seconds to shut down. Now I can take the time to examine what information it collected. Now, RagShot only collected information about changes to the system. So for example, if any temporary files were created, it wouldn't have seen them. But this tool actually shows me a full log of every single event that happened, especially when it relates to the file system and the registry. One way to look through this log file is to examine it and see, do I find anything interesting? You would ignore interactions with normal Windows DLLs, for example, and look for anomalies. The recent version of Process Monitor has this really neat feature under Tools that allows you to summarize the events that it observed. For example, you can look at process activity, and guess what? It'll tell you what it saw. The only change that it observed while it was collecting records was this process called Windows, which probably means Windows Live Messenger, running on the system. All right, that's not unexpected. How about file summary? This is kind of nice, because yes, the executable accesses a lot of files. That's normal for any Windows program. But you can look at the files by folder, and right away you can start noticing some anomalies. Like this file, pass.exe. You can see that it was created here. If you look at what's going on in Windows, you can see all the files that were touched, read, modified, executed while the malicious program was running. If you want to see how exactly this happened, if you want to see what events were associated, let's say, with access to the file called pass.txt, you just double-click. And, unless it crashes, it'll bring you those events right there to observe. Let's see, did it work for me? It's still thinking. So, let's see. Oh, there they are. Now I can see exactly what it did with that file. Look, it created the file, it wrote something to it, and then it closed the file. Again, in this case, we already observed something similar, but now we can see the exact circumstances under which the program was accessing that file, whether it was reading from it or writing to it. That's very nice, that's very handy, because there are some files that it might create as temporary files and then delete them right away, but you're not going to see that in Ragshot. So a nice tool to observe local file system and registry and some other activity. There's another tool that I thought I'd mention to you, and this is a tool that, again, looks at the state of your local system while you're infecting the box. So let's see. Before I run this experiment, let me clean up this box. By the way, now I kind of know how to uninfect the system. It looks like all it does when I run it is it creates this pass file. I'm going to delete it. And then the other file that that's in Windows, well, just to be sure, I'm going to replace it with a clean version of the file that I got from the infected virtual machine. I mean, from the infected system in the wild. Looks like it probably has not changed it. All right, I'm again repeating my experiment. Now, even though I'm not changing the state of the environment, I want to show you another really useful tool for monitoring process, registry, file system, and network level activity. And let's see. The tool is called CaptureBat. It's a freely available tool, runs on Windows, command line based. To launch it, you go to the directory where it installs, and you type CaptureBat. It accepts some optional parameters. For example, CaptureBat can act as a network sniffer. So if you wanted to monitor your network for you, you just type it -n, stands for network. CaptureBat also has a way of restoring files that have been deleted in the background. That's handy, because the recycle bin that's built into Windows only restores files removed from the GUI. What if this program removes some files and you want to take a look to see what were they like when they got removed? To do that, -c stands for capture. Capture deleted files. And now I press enter. You can see it's loading its drivers to monitor all the activity that's worth observing. The nice thing about CaptureBat in comparison to Process Monitor is that it comes with several filters built in by default that will try to eliminate normal Windows activity. There's much less noise in these logs. So if it shows me something, most likely it's a little bit anomalous. Notice this program has been already running for about half a minute, and it hasn't reported anything, because nothing strange was happening on the box. Now let me try infecting the system. I'm going to interact with it just like I did before. abc@example.com. Sign in, close, maybe exit. So it's going to launch the browser there. OK, I know you want us to go to this website. We're not going to. Now that I finished infecting the box, I can pause capture in CaptureBat as soon as it finishes logging. By pressing Control-C or by pressing Enter. All right. Now look what it's doing. All the logs that it collected about temporary files that were deleted, as well as about network access that it observed using its network sniffer. It's going to package it up as a zip file. The zip file should be here. It's called capture, and then it uses the date. So let's take a look at the zip file to see what was captured there, what files maybe were deleted or modified, and what I really want to focus on now is what network traffic was observed. Let's see if anything was observed. All right, so I'm going to open the zip file, go into the logs directory. You can look at deleted files, modified files. You can observe them. But what I really care about is looking at the pcat file that it created. Pcat file is a standard format network sniffer file. Any network sniffer is going to load it, whether it's Wireshark or Snort or TCP dump. I'm going to double click on it because I have Wireshark installed on the system. So Capture Bat is able to capture traffic, but you need another tool to actually interpret and observe what it has captured. All right. So let's wait a little bit. I don't have a lot of RAM assigned to this virtual machine, so my programs perhaps aren't as slow or rather as fast as I would like them to be. Oh, there we go. All right. So what's going on here? I can look at traffic. Right. This is Wireshark. It captures all the packets. A lot of them might be broadcast packets. The broadcasts occur on a Windows network all the time. I'm usually not too interested in them. What I always look out for are DNS packets. Take a look at this one. It's a packet that is coming from .128, which is my infected box. It is going to .1, which is the system that it thinks is its DNS server. And look at the payload of that packet. It is attempting to resolve the hostname SMTP 185.google.com. The easiest way to see this, if you right-click on the packet, you can say follow TCP stream, and that's going to show you all the payload that it saw. Looks like it tried to resolve this hostname twice. Why is it resolving the hostname? Well, probably because it wants to connect to it. Now, this is an isolated environment. It cannot connect to it. Also, in my laboratory environment, I don't have any services running. There is no DNS server. So that's why this DNS request did not get a response. But that's OK, because all I wanted to know is what hostname is it looking for? What does it want to use it for? Well, my theory is that probably it wants to use it as a mail server. Why? Because there's this SMTP as part of the hostname. But I don't know for sure. That's just my gut feeling. To know for sure, I need to allow it to resolve this hostname. Several ways of doing that. Let me quit Wireshark, because I've gotten as much as I wanted out of it. One way to allow the program to resolve the hostname is, of course, to edit the local hosts file. And you would say, oh, if you're looking for this hostname, here is its IP address. Now, which IP address are you going to give it? It's not very useful to give it the IP address of the real system on the internet that corresponds to this hostname. Because the next thing it's going to do, it's going to try connecting to it. It's going to fail because this is an isolated environment. And you won't have learned much from that experience. Much more useful is to give it an IP address of one of the systems in your lab. This way, when it tries connecting to it, you can run the corresponding service there. And then it's actually going to be able to interact with your host, and you will see what it's trying to do. Editing host files works, but I make a lot of typos. So I'm not going to do that here live while I'm doing this demo. Instead, I want to show you another really handy tool called fake DNS. It's a fake DNS server. This DNS server is fake because no matter what query you ask of it, it'll always going to respond with the same IP address. Yahoo.com, same IP address as Google.com, as MSN.com. This way, you can redirect all of this traffic to one of the systems that you control. The system that I control in this environment that I'm showing you now, it's just my isolated laboratory environment running a single box. So I'm going to redirect the traffic to localhost 127.0.0.1. To do that, not only do I open the program, but I also click Listen. Now, Windows Firewall is trying to protect me. Are you sure you want to launch a listener here? Yes, please unblock it. All right. Now, there's one more thing that I need to do to allow my DNS queries to be resolved properly. And that is I need to make sure that my that my Windows virtual machine that I'm infecting actually uses itself as the DNS server. So let's go to network settings, look at TCP/IP properties. And right now, this is the DNS server that it's using. Guess what? I'm going to just point it to localhost, which is 127.0.0.0.1. All right? I don't need to reboot. That's nice. Now, whenever I do this, then I try to confirm that DNS resolution actually properly works. So what I do is I go to the command prompt, and I query some host name. Let's say I do a ping my website, zeltzer.com. I'm getting a response from localhost, even though I'm not on the internet. And fake DNS actually shows you the queries and the responses that it is processing. This way I know that the DNS server is acting the way I want it to act. Now, what I hope is going to happen is that the malicious program is going to try to resolve that Google SMTP server's host name. And the response it's going to get is, oh, it's localhost. And if that's a mail server, it's going to probably try to send an email. So now I want to be able to intercept that email. And this happens often enough that I like having, as part of my toolkit, a fake email server. And that fake email server comes actually from the same source as fake DNS. It's made available by iDefense for free. It's called MailPot. MailPot stands for email honeypot. And all I got to do is just run it. Now it is listening. Well, as soon as I click the listen button, it's going to be listening on port 25. I'm going to unblock it. And now, theoretically, whenever somebody tries to send an email through my local host, it's going to capture that email. It's not going to deliver it. That's good. But it's going to capture it and allow me to see what's being sent out. So I got my fake DNS server set up. I got my fake mail server running. And now, hey, let's see if it works. Excuse me. All right, repeat my experiment. Now my environment is a bit different. Now it should no longer try to resolve the host name over the network because it should get a response from the local DNS server. All right, the email address I'm going to log in with is going to be hello. No, maybe not hello. I don't feel like hello. hi@example.com. La, la, la. All right, I click sign in. Hey, look at that. There was something sent. The thing is, for whatever reason, the number of bytes that was transferred in this particular situation is 0. Maybe it's a bug in the malicious program, because believe it or not, malicious programs are written by human beings who make mistakes and therefore have bugs in their creations. Or maybe it's a bug in MailPot, which is also, as far as I know, written by human beings. So that's OK. It didn't work this time. Let me try logging in again. Sign in. Oh, that looks more promising. Now I have actually captured an email address that has some bytes to it. So let's double click, and here is the email that it intercepted. Now our theory is correct. Not only does it create a local password file, but it actually takes it. This is the password that I typed. And it sends it out to masterclinics@gmail.com. It leaks out my password, my username, and it sends it through Google's SMTP server. That's kind of nice, because right away you found out what this program is capable of doing, and now you might start wondering if this is a serious incident. Was there a significant data leak here? Is it a big deal that somebody knows my logon credentials to MSN Messenger? But that's the idea behind behavioral analysis. We were able to learn quite a bit about this program without even looking at any line of code, by just interacting with it and trying to do the best we can by evoking new behavior. Whenever we saw that it is looking for some resource, like a DNS server or a mail server, we gave it that resource. And just so that you believe me, I actually have a slide that talks about this. You know, people say, where is it written that this is the way to do behavioral analysis? Here's the slide. And you continue to do this stuff, interacting with malware, observing what it does, until two things happen. Either you run out of time, because that's the reality. We oftentimes run out of time and need to move on to another project. Or there's nothing else that it does. There's no other way in which you can try to interact with it to get it to do anything else that's worth observing. And yet maybe there's something more that you want to learn about this program. And that's when it's time to move to code analysis. And in code analysis, you're actually looking at the assembly instructions that comprise the executable that make it do the thing that you observe it doing. You see, it's very possible that this program is capable of doing more than you just observed. Maybe we just weren't able to recreate the right environment, so it did not fulfill its true destiny yet. So we'll look at code analysis, and the tool of the trade here is a disassembler and a debugger. In my course, we cover several tools that help us with code analysis, but right now I just want to focus your attention on a very nice disassembler and a debugger in one called OllyDebug. It's free, it works quite well. Here's how we're going to use OllyDebug. Let me show you. For this, I'm actually going to quit my mailpot and my fake DNS server. I'm going to quit the other tools that I was running because, well, I want to show you something else. OllyDebug. It runs on Windows. It has a nice GUI to it. And the way you interact with it is, well, by using the various menu options. To start analyzing an executable, it's quite natural that you will want to load it. File open. We're going to point it to the executable that you want to study. There it is. Now, when OllyDebug loads an executable, it's going to process it. It's not going to run it. It's just going to examine it and then give you some time to take a look around to see what's going on here. OllyDebug, its screen can be a little overwhelming, especially because everything is in capital letters. It takes some time to get used to it. But the most important area for us to keep an eye on right now is this window here, because that's the disassembler. You see, a compiled Windows executable contains binary data that corresponds to instructions that the Intel CPU can execute. Now, most human beings can just look at those instructions, even if they're in a hexadecimal form, to understand what they do. For that, we have a tool called a disassembler. So this is the disassembler built into OllyDebug. You see, it looks at these hex values, and it translates them into something that's easier for us to read. That's the assembly language. Now, the good thing is that you don't need to be an expert in writing assembly to understand what goes on here. You just need to be good at reading it, or at least know your way around it. So it helps. But in my course, I show you just what you need to find your way around the program. Right now, though, I'm not going to overwhelm you with assembly code. Instead, I want to show you one way in which you might start analyzing this program. We're not going to get too deep in it, don't worry. One common way of starting the analysis of a malicious executable is to look at what strings are embedded into it, and then find code that processes interesting strings. To look at strings embedded in a program with an OllyDebug, I right-click on the disassembler area. Then I go to search for, and I say all referenced text strings. This is going to try to locate as many strings as it can within this executable. Scanning it, and here we go. Here are all the strings that it located. I can look at it and say, some of these are interesting to me, some of these are not. Now, keep in mind that some strings might be embedded into the executable just to confuse you. And maybe no code is actually using them. But in this case, I want to show you, let's say you have a string like, I don't know, MSN settings. Right? Remember, that was a file that was created and presumably read when the malicious executable was running. Let's say you want to locate code that is making use of this string. To do that, you click on the string, and you press Enter. Now it jumps to the disassembler, and you can look at the code that makes use of the string MSN settings. And if that's the string that you really want to understand, how does it use it? Why? Under what circumstances? Well, here it is. You just spend some time analyzing the code, and you will see how it processes that string. Now, we don't have much time to spend on this topic now, so I'm not going to drill into this particular code, because I think there's something a little bit more interesting that I can show you. And here's what I'm going to do. Now, remember, there was this string in a file, MSN settings. Now, what's interesting is that on the live box in the wild, that string on the top of the file was test, T-E-S-T. The reason I think it's interesting, not because a test is interesting, but because when you ran the program within the lab without MSN settings file, it created this file with a different value. The value was hello. That's a little bit weird. Why would it do that? What's the significance of hello? What's the significance of test? Let's try to figure that out. Where do you start? If you look at the strings embedded into the executable, you're actually not going to find the string hello embedded into it in clear text. It's not that simple. That's OK. Because the technique that I want to show you involves a powerful feature of a debugger called memory breakpoints. What I'm going to show you how to do is to use OllyDebug to look in memory of the malicious process, locate this string in memory. It will exist there because it's using the string, so it's going to have it somewhere in memory. And then I'm going to set a breakpoint on that string. It's going to be called a memory access breakpoint, which means that the program is going to run normally. But as soon as OllyDebug observes the malicious program trying to access that part of memory, trying to use the string test, it's going to pause. That's called a breakpoint. And now I can look around and figure out what's going on. So that's the technique that I want to show you. It's pretty powerful. How are we going to do that? Well, let's start by launching OllyDebug and loading the malicious program into it. Now, right now, you will notice that the program is paused because OllyDebug wants to give me a chance to look around. But the thing about this technique, the thing about locating strings in memory, is that the program should really be running because it probably has not yet loaded that string from the MSN settings file just yet. So I'm going to click Run. To do that, I go to the Debug menu and say Run. And guess what? The bottom right corner of OllyDebug says Running. That's good. So what this is doing is it's actually running, but within OllyDebug. And presumably somewhere behind the scenes, it loaded MSN settings, and somewhere in memory, it loaded the string test from that file. I want to use OllyDebug to locate where is that string in memory so I can locate the code that is processing it, so I can understand the mystery of hello and test. So to do this, once the malicious program is running, I go back into OllyDebug. I can still interact with it. And I press Alt-M. M stands for memory. Alt-M brings up the memory map. This is the map of the memory of the running process that I'm currently debugging. This is where you would locate all the DLLs that it loaded and the code of the malicious executable. And also, you will locate, hopefully, all the data that this program is currently loading or processing. Now, in OllyDebug, where do I look? There's a lot of memory to search for, about 4 gig in this case. So what I'm going to do is I'm going to use a feature of OllyDebug called binary search. To bring up binary search, I press Control-B. B stands for binary. In OllyDebug, there are some command line there are some right-click options, but you know what? The most reliable way to search is using shortcuts, because these options that you see here, they differ from screen to screen. Shortcuts tend to be much more predictable. So actually, on my website, I have a cheat sheet that you can download with all these shortcuts. Search, or Control-B, will bring up the search window, and I'm going to search for the string that I care about, that string that was embedded in the file that I'm hoping to understand why it's using it. Test. Now, the string test could exist within the process memory in several places for several different reasons. Let's see what happens when I click OK. I'm searching the entire block of memory that's associated with this process. Searching, it's searching up, and it brings up this area. And take a look at this. You see, there's a string that it found in memory called test theme background. That's probably not what I'm looking for. This doesn't seem right. I'm looking for the string test that's standalone. It makes no sense that the program would use that string to combine it with test theme background. Maybe I'm wrong, but you know, sometimes you go on a hunch, and if it doesn't work out, you repeat this experiment again. So I'm going to repeat my search. I want to search for another instance of the string test in memory. To do that, it's a little bit tricky because you need to remember to go back to the memory window, click on the top, and now to repeat the search, you press Control-L, L like Lenny. Why Control-L? I have no idea, but that's just what it is. Control L repeats the previous search, and oh, I found it again. All right. Let's try it again. Maybe it's because I put my cursor all the way to the top of the memory file. Maybe I just need to continue searching for where it stopped before. Control L again. OK. Now, this looks a little bit more promising because it is a string test in all lowercase by itself, just the way it is in the MSN settings file. So now that I think I located the likely string, what I'm going to do is I'm going to highlight it, the 4 characters that that are associated with it, highlight it, right-click on it, and say breakpoint, memory on access. When I do this, I'm going to tell OllyDebug to pause executing this program whenever it notices that the program is accessing the string test, this particular part of memory. Click. No visual indication that the breakpoint was set, so let's hope that I clicked correctly. And now we wait and have a beer and relax. Or perhaps a bit faster will be to try to interact with the program the way the victim is expected to interact with it. Click on some buttons, type some stuff, because clearly by just waiting, we're not triggering the breakpoint. All right. So what I'm going to do is I'm going to start typing the email address here. And I don't know what to type here. I'm going to type character G. I don't know, G. Hey, look at that. It paused executing the program as soon as I typed a character. And it brought me to the piece of code that is processing that character. So now we need to do a bit of assembly analysis. And I know we haven't spent time talking about assembly, so let me walk you through the most important aspects of this, because this is not the easiest thing to look at. It is highlighting the next instruction that the program is going to execute. Here's the string test. It exists within the program's memory. And you can start executing this program one instruction at a time until you observe something that's interesting, something that kind of rings a bell in your mind. This instruction here that I'm looking at right now, it doesn't seem exciting to me. I don't know. There's no insights that I'm gathering from looking at this particular instruction. So I'm going to allow this program to execute one more instruction. To do that, I say debug, step into, which basically means execute another instruction and then pause. You see, I'm able to use OllyDebug to slow down the execution of the program to as slow as one instruction at a time. OK, how about now? Well, here's my disassembly code, but take a look at what's at the bottom here. What it shows me is what data it's operating on. What it shows me is that this instruction that I'm looking at right now, it's called CMP. This is a compare instruction. It compares some data. It is actually comparing 2 characters. And at the bottom here, OllyDebug tells me what characters it's comparing. The character T to the character G. Now, character G happens to match the character that I just typed. Character T happens to match the first letter in the word test. Interesting. Now, a bit more insight into this. CL is a register that matches one part of the register called ECX. There are several specialized CPU locations on an Intel processor. They're called register. They're very fast when it comes to data handling. And OllyDebug shows us these registers here. CL refers to parts of the ECL register. And you can look at that content of the register here, but usually you get more insight if you double-click on it. Look at this. ECX register contains in it the character G. What about the other register that G is compared to? BL. BL is actually part of a register called EBX. Double-click on it. Yeah, look at that. TSET. It's the word test backwards. This is starting to look interesting and promising. It's comparing the first letter that I typed to the first letter of the word test. Interesting. Let's do this again. Let's see what happens if the 2 letters match. Let's say I type T. What's going to happen next? You see, I'm able to interact with the program and try all these scenarios and repeat it and undo it. It's my lab. I can do whatever I want. So I'm going to click cancel. Right now, the program is paused, so I cannot interact with the malicious executable. I'm going to click debug run to allow the program to continue running. I'm going to back to the login window. And now, I'm going to see that instead of typing G, I'm going to type the character that I think it is looking for, the letter T. Let's see what happens. I should trigger the same breakpoint again. Let's see, T. All right, here I am, the same area of the code. And let's look at this comparison function, debug step into. It's comparing T to T. OK, that's interesting. Now it's going to do probably something different because the two characters match. They're equal to each other. So I'm going to continue stepping through this program one instruction at a time until I observe something else that's worth talking about. So I'm going to say debug, step into again, or I can just press F7. It's a little faster. Nothing interesting that I could see. F7 again. F7 again. I don't see anything worth observing. Oh, look at this. There's another jump. How about another 7? This isn't what I wanted to show you. That's the trick of performing this lab live. So let me try it again, because when I did it in preparation for this talk, I experienced something a little bit different. So let me try this again. I continued to run the program. I'm going to click T again. Let's see, maybe I just missed that part of the code that is doing something interesting. It's comparing T to T. All right. Ooh, what's going on here? All right, guys. I just may need to revert to slides. That's why I take slides. Because what's happening here, what it normally does, after it compares T to T, there's this other instruction that it executes. It's an instruction that compares two other parts of the registers. And if you double click on those registers, you would see it's comparing the letter. Oh, I know what I was doing. I need to type a second letter, because T matched to T. What about else? Something else. All right. So T matched. Good. How about another letter? I'm going to type A. I should trigger this breakpoint again. Here we go. We're paused again. Now, if I press F7, I should end up here on the second comparison. It is looking for E. I typed A. BH is part of the EBX register that contains test. E is the second letter in the word test. I typed A. So what's it doing? It seems to be comparing what I typed to the word test. I don't know why, but let's see what happens when I do type test. So you know what? I'm going to allow the program to run, but now I'm just going to experiment with it without the debugger, because I don't really need the debugger for the next step. So I'm going to exit it and launch this malicious program by itself. And now I'm just going to type test. Let's see what happens. Test. Haha, look at this. We've reached a secret screen. It looks like this is the configuration screen of this Trojan. This is the screen that allows its operator to define this password test. It's presumably hidden, concealed somewhere. Well, maybe it's not really concealed. It's probably just saved to the MSN settings file. It allows us to define several options about this program, like what to do once the sign-in is clicked. Right now, it's showing us an error message, but we could just terminate the application. If we click on Other, look at this. We can define where it's going to leak our data to. So this is a configuration screen. It seems that this information is stored within that MSN settings file. But if we just looked at the MSN settings, excuse me, at the MSN settings file, we might have a hard time interpreting some of the contents of it. Now we've found the secret screen, and it's always fun to find the secret screen. So that's why I thought I'd show this to you. And this is just one of the many techniques available to you with a debugger that allows you to really just look very deep into the program and just take it apart and explore what it is capable of doing. So far, we've just analyzed a few aspects of this program. Of course, you could have looked at other areas of the program to see if it's capable of doing anything else. We determined that it's a keylogger, determines our MSN Live credentials. We determined that it saves them to a local MSN, to a local pass.txt file. It leaks them out to a particular Gmail email address. And it's configurable using this secret password of test. But you can probably change that by editing the MSN settings file. And that's as much as I want to say about this program, because that's as much time as we have to cover this topic. Why is it useful to do this sort of stuff? I mean, besides the fact that it's kind of fun. Well, because now we have an ability to work with our incident handlers, to work with our forensic people, to tell them what else to look for in the infected system, to tell them how to prioritize this incident. And sometimes, if you're a one-person shop, sometimes you're giving all these answers to yourself so that you can figure out what is the nature of this incident. We employed several techniques that I think are core to a sound reverse engineering process. It involves observing how malware behaves, but not just observing, actually trying to interact with it to evoke additional characteristics. And we also used just one of the many capabilities of a debugger to peek into the internals of the malicious software. It's kind of fun to try to do this in your lab. That's why if you go to the URL, tinyurl.com/malcast, you can download this presentation with my full speaker notes and instructions. And also on that page, you can download this malware sample that I was analyzing. Now, be careful, take the right precautions that I talked about, isolate it, experiment with it. And if you like this sort of stuff, you might like the cheat sheet that I mentioned earlier. You can download it from my website. It has common shortcuts for OLE debug and various other tools that are useful for reverse engineering malware. Of course, if you like this sort of stuff, you can take the full multi-day course that I teach at SANS, the reverse engineering malware course. And I do have a discount code that I can share with you if that's something that you think you can benefit from. People tend to like this course because it is able to cater to different backgrounds that people bring into the classroom. And it's really a good way not just to learn from me, but also to learn from each other, because everybody who comes into it has different experiences and different tools and different approaches. And the way my course ends up expanding is by really getting feedback from people like you. So if you have any questions about what I did, if you try to repeat these steps and you get stuck, send me an email to lenny@zeltzer.com or talk to me on Twitter, twitter.com/lennyzeltzer. That's as much as I have prepared. Drop me a note if you have any questions, or come over and we'll talk. Thank you very much for your attention.